Hello, everybody. My name is Linda Sheard, and I'm very pleased to be here today. I think I do want to start with an introduction of who I am. And my clicker doesn't work, so that's a great start. Let's try that again. No. All right. I guess I'll be here. Why am I here today? In terms of introduction, you can see there's a lot of professions on my CV. And what you should take from that is that I'm keen to get into new things. And my background more recently was really in the big data analytics and AI space. And I'm here really to start conversations about my observations of working with a lot of the organizations that are represented in the room around the challenges of working with geospatial data in a number of contexts. And at Microsoft, I've had the privilege to work with a bunch of you on exactly those kind of growing pains that are going in different directions in this space. And my particular interest is sustainability and the kind of AI for protecting the planet, carbon capture, placement of wind farms, and lots of cool projects that I'm happy to talk to anyone at length this evening. So my target audience today really is two groups, and I'm hoping that I'm capturing quite a lot of you with these categories. It's either people who come from a data science background and want to bring machine learning or even computer vision to the geospatial domain. And I don't think we've touched on computer vision much yet. It's a big topic in this space around working with the plethora of remote sensing data that's now available. Or I'm talking to the geospatial subject matter experts that really are exploring more programmatic approaches to working with data because they're realizing that the world is changing. And I'm slightly apprehensive to say in an establishment like the Royal Geographic Society that visual analytics is not the answer to dealing with the huge volumes that we're working with these days. If you think of Thusal's talk earlier, he showed a great visualization at great detail of showing us millions of points on a picture, but that was the output. That was not the analysis. That's the post-processing to communicate your results. So the question for me is, where do we do that processing that really manages to process data at scale? And we've had the great talk from Kato just now because Kato has realized that CartoDB running on a single server on its own is going to burst out of its boundaries if it's trying to address bigger data sets. Whereas if they push down some of those things that you can trigger from there onto the lake houses, the data lakes, the big data analytics patterns, then you can start to grow beyond that. So I'm really here to talk about that layer. What can we do in the big data analytics space? And so just to start on that, I'm guessing that a lot of you are familiar with the bottlenecks that tend to be your machine. You might have been given an amazing super Mac or something, but that's still often not big enough for us. It's your internet connection if you have a pattern where you're downloading data to your local machine to then run your models or run your analytics. And for that reason, you probably also have a secret data stash on your machine that you work with day to day that's really valuable, but no one else can see it. So I want to start with some fundamentals. We've heard a lot about lake houses. My one advice is work with any kind of cloud-based storage. It doesn't have to be a lake house. It doesn't have to be a data warehouse. But make sure it's a data lake or data storage of some kind. How is that different from you're saying you're working off a shared drive? OK, well, a shared drive does allow you to share data, but that's about where it stops. I'm not going to go into the details and benefits of cloud data lakes, but the one that's important, I think, is that these are technologies that are really designed to be performant for analytics queries where you bring compute to the data, so you're not working on your laptop. And what that means is your laptop becomes somewhere that, yes, maybe you're allowed to upload data to this location, but you certainly shouldn't be downloading it. So what's your laptop for? It's a browser for web-based profiles, like CartoDB's interface is one example. There are many GUIs that allow you to interact with cloud compute. It can become a development environment that you can back with a cloud compute. Or it's an explorer for the storage, so you can have local applications that allow you to manage data. And the other thing I want to say about the data lake, it's up to you how much of the lakehouse pattern, for example, you implement. One pushback that I often hear about data lakes from organizations is, oh, but doesn't it turn into a data swamp? I would say that's kind of similar to saying, I'm not going to put a shed in my garden because I'm going to turn it into a dump for everything I own. If your organization is like that, then I'm not talking to you today. I am talking to the people who really appreciate a nice breadboard of all the different tools hanging nicely orderly on the wall, and you can use the right tool for the right job that you're doing in your data lake, in your shed, at this point in time. So let's look at some of those tools. We have serverless functions. You don't worry at all about what kind of machine operating system sits behind that. We have virtual machines. That is the equivalent of your laptop, but in the cloud, and you can pick different sizes of it, different configurations. We have clusters of VMs that are clusters of the same thing that you can do parallelized jobs on, and we'll come to that. And we have more sophisticated clusters that come with a scheduler and that allow you to run even more complex types of distributed jobs. So just a very quick parallelization 101. We're looking at, there's more complexity here, but I just want to keep it simple, just as a baseline. If you think about the types of ways that you can parallelize operations across processes, even on a single machine, you have data parallel and task parallel. And if I just give you two examples, the data parallel might be something like you're working with raster data that for every pixel has an RGB infrared value, perhaps, and you're computing something like the normalized vegetation index, the NDVI. That's a computation that is entirely independent of the other pixels in that raster, and that means the process is not affected at all if I chop that up into lots of data chunks and I calculate that on each little chunk. Another example like it is machine learning inference. I have a model already. I've got a new data point. I send it to my model. It gives me an answer. I can do that in parallel on a data parallel kind of pattern. The other side of it is task parallel. And a good example of that might be where I have a machine learning training data set that I've created. It's probably pretty big. And I want to train a new machine learning model. And I might do what we call a grid search across hyperparameters. That means I run many different machine learning algorithms over the same data set to see which model performs the best. And that's an example of a task parallel type system. Now, parallelization can be on a single machine. Distribution is where it gets interesting. It's where we do that across different machines that the cloud can give us. And you'll remember that picture that I showed you of clusters scaling out into multiple machines. And what I want you to take away from this is that there's many different frameworks for distribution, and this is by no means complete. But what's important to understand is that on the left side of the scale that I'm showing you here, we've got the kind of distribution that's really good for the sort of data parallel thing that I showed you earlier, which is very relevant in service load distribution. So we had a colleague from Allegro talking about building microservices, integrating IoT data. I've got lots of calls, and I need a system that can respond to the calls by scaling out, but all the processes are doing the same thing. In the middle, we're talking more about big batch parallelization. I might want to process a whole set of raster data, or we're talking about that kind of machine learning training that I talked about earlier, where we might want to run multiple parameter optimization modeling processes on multiple machines. And then all the way on the right, we've got complex in-memory computation that something like Spark can give us. And this is where I come back to my two audiences at the beginning. If I've got audiences if I've got people in the audience who are data scientists who come from Python and are starting to work with vector data, what you might be finding is that you're probably going to have to go into PySpark and Scala to address the difficulty of scaling geospatial vector data. Because this is where geospatial is a bit counterintuitive. If you're coming from single-threaded machines, then joining a data set of many, let's say many points, to, let's say, a single row, a single polygon, many to one, sounds easier than many to many. The reality is that when we're working in Spark, that picture is completely different, and actually the many-to-many join gives you much better performance. And this is where we come around to indexing. So I'm hoping, in the spirit of spaced repetition, I'm going to repeat some of the concepts that have already been talked about a lot. I'm not going to talk about hexagons, so that's exciting. So two things. I want to talk about geospatial vector data input-output, so I/O. And the question there is, how do I get those? So Javier talked about GeoParquet, for example. which is very amenable to distributed data sets. But how do I get from my stack of shapefiles or my stack of GeoJSONs or GeoPackages or whatever it may be to that point where I've loaded all of those shapefiles into my distributed memory in my Spark cluster? So this memory that I can now operate in is bigger than what I have on my laptop. It's however many machines I want, and there's their memory joined up that I can do computations in. So we're going to talk about that, and then I'm going to touch on geospatial joins, which is the indexing topic. So one example that I've been working with a little bit is the Inspire index polygons data, tons of GML files, really hard to get a handle on, and we did some great collaboration with some folks at DEFRA and with Databricks also to look at how to approach this. And I just want to go through this just briefly. Let me find my laser pointer. So the idea is you have files in storage that might be of varying sizes. And you have a Spark cluster that, if you remember earlier, has a bunch of workers, and it has a scheduler. And the principle here is that we define what's called a user-defined function. Now, all you Python developers, this is your favorite thing, because a user-defined function allows you to write standard Python and essentially do what we said earlier, do a data parallelization. So you can run your function in parallel over a whole bunch of data set that is much bigger than what you could normally do. So it's an easy way to get into PySpark, essentially. So here, what this function does is it reads a portion of the file. It might read the whole file. It might read a portion of the file. But the outcome is that we have all the data from all the files in our distributed in-memory Spark dataset. Now, what have I got over here? Just to reference back to what Javier was talking about, what we want to do is, once I've done some computation, I don't want to store this back into these tedious little files. I would like a format that is very amenable to reload that data quickly. And so Parquet is a really good format for that. And the current limitation is that we, at this stage, lose the geospatial metadata, so we have to keep note of that somewhere else. Whereas with GeoParquet, and Javier is smiling because it links together very nicely, that would solve that little gap there. That's pretty important. OK, so that was I/O for the data scientists. Let me briefly talk about indexing. We've talked about it a lot today. The one thing, if you take away one thing from this that I want you to take away, is that I'm talking about indexing for performance optimization. And that means there's no opinion as to how you end up presenting your data. So there were a few questions around, should we be worried about my hexagon representing different sizes of populations? That is still your choice. And I want to advocate for responsible use of hexagons, just like we have responsible use of AI. Because what we don't want to end up with is the equivalent of the postcode lottery. I happen to sit in the hexagon that someone's calculation has said has certain attributes, and that then gets used in some insurance process or something. So you as data scientists, it's your responsibility as to how far you want to go. And we'll see in a minute exactly where. So before I get into that, I just want to quickly contrast traditional indexing from traditional database systems with the indexing that we've talked about today, which is about patches that we polyfill our polygons with. What we used to do is we used to have something called, one example, R-tree indexing, where we say, build an algorithm that finds the least overlap of grouping together multiple polygons. So this might be one example where this is kind of the best you can do. If you split it any further, you have big overlaps of rectangles. R-tree stands for rectangle tree. And then I might do the next thing, one back, it's called a tree because I can do this recursively. So now I can find the smallest rectangle that, with the least overlap, bundles some of these rectangles. And the way this works is I have my system that is not a distributed system, and I want to make a query of this data. And the way that this works is my index tells me I don't need to bother looking in R2 if my query area, the area that I'm looking at, doesn't intersect with the rectangle 2. So in my database, I know I only need to go and search within rectangle 1. So it's a process by elimination. That's not a process that works very well if you've got something like a flood zone, or someone else was talking, Stephen Bell was talking about linear geometries that intersect tons and tons of polygons. I'm going to have to bring all of that data onto my compute to actually do whatever computational query I want to make to do. And that's where I'm probably crashing. So instead, what we look at is some sort of polyfill indexing. I've gone with squares. I said I wasn't going to talk about hexagons. Doesn't matter what it is. The benefit of understanding it at this level is that you can use your own indexing system if you're working at the level of PySpark and you understand the logic behind this. And I want to go through this really quickly. The concept is that you chop your polygon up into whatever your index is. You end up with polygons that you know, with squares or patches that you know are fully contained within your polygon, and others that you know are on the edge. And that is all you need to know to create equality relationships that give you two areas. One is the minimum size overlap, which is the green, and one is the maximum size overlap, which is the blue. And if your data and your use case is such that that is good enough for your analysis, then you can stop there and you can plot this result. The important part, and you can join it with other data and lots of things that we've seen today based on hexagons. The important part is that you can go further and compute the exact intersection for the squares where there are borders of your original polygons. That means you're not throwing away the original data, and you can go back to an intersection where you've actually identified the precise intersection, and you can plot your final data on that basis. So this is what I was talking about when I was saying it's your responsibility to figure out how far you go with that. Three things that I want to point out. The first one is the DEFRA team that I mentioned have open sourced their library for reading various types of geospatial files into PySpark data frames. It's a very early stage library, but please use it, comment, get involved, build a community around it. We've heard about Mosaic today. If anyone wants to weigh in on Miloš, I don't know if he's still here, that we push hard for the British National Grid Indexing System to also be supported in that. I think it's a really great example for endorsing that WGS84 is not always the answer for the high-resolution use cases. And I also want to mention Esri, who have published something called the ArcGIS GeoAnalytics Engine, which again is a library that you can install on Databricks. And similarly to what Kato is doing, it acknowledges that some of this processing needs to be done on that sort of big data distributed architecture. So just to link it up with everything else that we've seen, what I've been talking about is if your big data architecture happens to be Azure Databricks on, I'm supposed to see it Azure since I'm in the UK, sorry, I've been trained. Sits on Azure, then that would look like on the left. And you can work with that directly in PySpark and notebooks. So this goes out to all the people I was seeing who were on Jupyter notebooks when I was sitting at the back during the conference. And if you want to go further than that, then obviously that's exactly where the toolbox that we just saw also plugs in, which I thought was a really interesting outcome. So with that, I think I'm at time. I have some content about responsible use of AI that's much more general, and I'm going to refer you to a presentation I'm giving next week so that I don't take up too much time. I do want to thank all the folks that I've been working with, primarily the Ordnance Survey, also DEFRA, and also Miloš, who we've been collaborating very closely on the hacking away at the Mosaic concepts. For bringing me into this domain. I think it's an incredibly exciting domain, and it's only going to get bigger. Two calls. I'm trying to set up something called the Azure Geospatial Interest Group. There's not very much there yet because it's just me, but any of you who are interested in working on Azure on some of these things and get things working, please get involved. I'm lying, it's not just me, but there's a bunch of stuff that's not public yet, so keep an eye on that. And with that, my preferred method of contact is LinkedIn, so do connect and leave a note as to why you're connecting. Thank you.